All right, hello everyone, and today we are going to be finishing our discussion on graphing radical functions. So grab out a piece of paper, something to write with, perhaps a calculator if you need, and let's get into it. So last week when we started talking about um, our radical functions, we started to talk about the square root graph. F of x is equal to the square root of x. And this is going to be our parent function for a square root or a mother function, as we have put last week. As you can see on the right over here, we have our graph starting at 0, 0, 1, 1, 4, 2, and 9, 3. The way these points were derived is for every x value we chose, we got out the output. So for example, when x is 0, f of 0 is the square root of 0, which gives us our output value of 0. So that becomes the point 0, comma 0, which is what we called our locator point. That is the official start of our square root graph. And then we continue to choose x values that we could take the square root of. So the next one we could take the square root of is 1. So when x is equal to 1, we have f of 1, our function evaluated at 1, is equal to the square root of 1. And the square root of 1 is just 1, so our output value is 1. So we have the point 1, comma 1. The next number we know the square root of is the square root of 4. So when x is 4, we have our function evaluated at 4, gives us the square root of 4, which we know to be 2. So our x value is 4, our output y value is 2. That leads us to this third point, 4, 2. And another very easy square root we know is the square root of 9. So we chose x is equal to 9. When we evaluate our function at 9, f of 9 is equal to the square root of 9, which we know is equal to 3. And we get this cyan colored graph. Here's our locator point 0, 0, 1, 1, 4, 2, 9, 3. Way back when we did some noticings and wonderings, you guys noticed that is a curved graph with all positive x values and all positive y values. A bunch of you also noticed that the x's increased faster than the height of the graph. So like it went from 0 to 1, 1 to 4, 4 to 9. That jump between the numbers was larger than the height of 0 to 1, 1 to 2, 2 to 3. Which is really cool. So what we're going to do in today's activity is we're going to transform this square root graph based on AH and K values. It's really important. We know that this is what the square root function graph looks like, and it's very important we know at least 3 points of precision. So what I mean by 3 points of precision is that we know at least 3 points on the graph. Namely, the easiest one to know is 0, 0, 1, 1, and 4, 2. If you remember 9, 3, that's cool. If you don't, that's cool. 3 points of precision will be what we need to transform our graphs. Last but not least, since this is the parent function, it's important we understand where our domain and range comes from as well. Domain is x values, range is y's. So our x values start at 0 and continue all the way along this towards positive infinity, which is why we have 0 to positive infinity. We have a closed bracket, meaning we include 0 because this point is defined on our graph. And similarly, the range is y values. So we're going to read the y-axis from bottom to top. Notice there is no graph down below. There's no square root graph living down here. So our graph starts at 0 and continues all the way up the y-axis as well towards positive infinity. We're going to include 0 in here with a closed bracket because the point 0, 0, remember, is our locator point. So let's go and move on and talk about some more things in our graph. A quick reminder, last week we talked about the transformations of the square root and we practiced coming up with the descriptions and also a matching activity, which is pretty cool. You guys rocked it. For transformations of square root functions, again, notice that we have the square root function represented with the square root here. And we have a values, which are in the front of the radical, being multiplied to the square root. It's a times the square root of x minus h. Minus h, we have a horizontal shift here, which denotes left or right, opposite of what we think. Remember, it's next to your x. You can never trust what your x says. Do the exact opposite of what they say. Believe the exact opposite of what they say. And then we also had this k value outside of the radical, which is very direct. It's a vertical shift with a k. It's always going to be outside your radical, and it's exactly as it says it is. So plus k would mean up k units, minus k would mean down k units. So let's watch this quick little clip about how to transform square root functions. I did post this on Canvas, but just to make sure that we see it and see how we're going to use this to transform our function, I just think it would be really nice for us to watch it. It is like a couple minutes in length. It's really quick, and it shows exactly actually what we're going to be doing throughout this activity. Let me make sure I have. Let me make sure that I have actually my sound being shared. All right, here we go. And let's watch this full screen.
We're going to be talking about graphing rational equations using transformation. First, we want to take all of this information right here and look at the steps, and it says to sketch the graph of the parent function, which in this case is y equals the square root of x. And we want to sketch another graph for each level of complexity that is involved in the problem. And what I mean by levels of complexity are the scalar multiplication in front of the square root symbol, a vertical shift, which would be an adding a number outside of the square root symbol, and then a horizontal shift, which would be adding or subtracting a number inside the square root symbol. So we want to start off with this, and this graph right here is actually the graph of the parent function, which is y equals the square root of x. And that is because it has a point at 0, 0, because the square root of 0 is 0. The square root of 1 is 1. The square root of 4 is 2. And the square root of 9 is 3, which is slightly off the graph, but I'm going to graph anyway, because if we have a left shift, then that point could very easily come back onto the graph.
So notice here that they start off with the graph of the parent function. The graph shown in red is f of x is equal to the square root of x. And he briefly described how these points were derived. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. Now let's observe and see what he will do with these points from the parent graph.
So we're going to graph 2 times the square root of x. And this 2 in the front will take all of the y values here and multiply them by 2. And that'll basically make this graph taller. So we start with 0, and when we multiply 0 by 2, it's going to get me 0. When we multiply the 1 by 2, that'll get me up here to 2. And then when we multiply the 2 by 2, we'll go to 4. We multiply the 3 by 2, and we'll go to 6. And then this would be the graph of 2 times the square root of x.
So notice that here we have an a value of 2. So remember, a values are multiplied to the square root of x. I also want to draw your attention to the fact that we have a function that is being represented as y equals. So if I'm going to multiply 2 times the square root of x, it's only affecting the y value, which is why it only affected the height on the y-axis. Let's continue and see what else we can find.
Now, if we have a number outside, we want to make this a vertical shift, and it's going to do whatever it says. Plus 4 will go up. And so we take our parent function, we plot our points on there, and we graph it in. And then we're going to make all the points increase by 4 because of this plus 4. So we say 0 goes to 4, 1 goes to 5, 2 goes to 6, and 3 goes to 7. And we would plot our points in here, and this would be the graph of the square root of x plus 4.
So again, notice that we have a k value, a vertical shift of +4, meaning that all of the points were shifted up 4 from our parent function. So if you notice here, first this point was 0, 0, right? 0, if we go up 1, up 2, up 3, up 4, here's my next point. Again, from this point, 1, comma 1, right? Go up 1, go up 2, go up 3, go up 4. All of those points were just shifted. 4, 2, right? Up 1, up 2, up 3, up 4 units. And then this one was again 9, 3, up 1, up 2, up 3, up 4 units. So since it is a vertical shift, it only affects a vertical value, which would be y values or vertical. Again, so that's why it only affects the y axis. And y is equal to the value of the square root of x plus 4 shifted up 4 units. Let's see what other examples this video has in store.
Now, if we're going to do one that has multiple shifts, this one, for instance, has a vertical shift of +4 and a horizontal shift of a +2, which will actually end up sending it to the left. So what we're going to do is we're going to start by plotting our parent function. We get our points on there, and we'll pick one of these two things to start with. I chose the +4 since we just did that in the previous graph, and that's going to send it up 4, just like what we did. And this would be the graph of the first step. Now we want to look at the other information in the equation, which is the +2. And that +2 right there is going to shift all the points to the left 2. And this would be your final answer since we've taken care of all the numbers in the equation.
What I'd like to mention here is he just chose to do the vertical shift, the +4 first, and then the horizontal shift of +2 next to the x. Remember, go opposite direction of the x, so left 2 units. But really, the order doesn't necessarily matter here. So if you want to work from the inside out or outside in, both are the same. Let's see what else we have here. I think this video has one last example with a vertical stretch put in with a few of the other transformations.
Just for a more complex equation, this one has three types of things. It has a multiplication, it has a number on the inside, and a number on the outside. So what we are going to do here is start with the parent function, and always start with the multiplication. Multiplication says to make all the points twice as big, so it's going to shift it up just like in the first example. Then on the number on the inside, that is going to shift it to the left 2. So all those points will go left 2, and this would be the next layer. And then the last step would be the -4 on the end, which will shift the whole graph down 4. And this would be the final answer of 2 times the square root of x plus 2 minus 4. Today we're going to be talking about graph.
Okay, so in that last example, you guys will notice, let me just drag it back over there. On the last example, you'll notice that again, we started with the graph of the parent function. And first, when you have a multitude of things, or at least an A value, an A transformation, make sure you do that transformation first, that vertical stretch or that vertical compression first. So make sure you multiply first. Think of like the order of operations, PEMDAS. You would multiply before you add or subtract anything. So make sure you're applying the A value, then the H or K in any particular order that you would like. This, in his example, he chose to go from left to right, which is how I personally choose to do my graphing, just because it's consistent with everything else that we do in class. So now that we kind of have an idea of how we're going to approach these transformations, let's do a couple of examples. Again, the very first thing that I want to just review real quick is in order to do these transformations. First, we need the graph of the parent function, which is why it's so important that I brought up that we know what the graph looks like and we know at least 3 points of precision on our graph. Then we have to determine the type of transformation depending on the level of complexity. Is it just a vertical stretch or compression? Is it a horizontal shift? Where is it going? And does it have a vertical shift and where is it going? And lastly, you're going to shift and sketch the points from the parent function based on that transformation.
Today we're going to be talking about graph.
So here is our first question. And my question to you is, we have the graph of y is equal to the square root of x minus 1 minus 4. And which graph matches the equation? Is it graph number A, graph number B, or graph number C? Well, let's sit here and let's think about what we have going on. As I'm looking at this equation, I realize we have an h value of -1. H is -1, which means we're actually going to move right 4 units. Or I'm sorry, right 1. The -1 means we're going to go right 1 unit. And additionally, I observe and notice that there is a -4 value where the k vertical transformation is. So that means we're going to go down 4 units. So from our locator point of our original graph, from 0, 0, our graph needs to go to the right 1 unit and then down. So remember, if I'm looking at graph A here, 0, 0 is right here. So I need to go to the right 1 unit, which appears to be right here, and then down 4. So although this graph did shift down 4, it looks like it went to the left. So it's not graph A. Again, graph B, 0, 0 is somewhere around here. Going right 1 unit would be anywhere along this, and then down 4. Here's down 2. Here's down 4. Aha, here's my new locator point. So it appears that our solution is actually graph B. But let's double check and make sure that graph C doesn't work. So far, it looks like B is going to be the one. Again, here's 0, 0. We have to really interpret our graph of where things are starting. And the graph actually goes left. So it's not C, it's not A. The answer to this is B. So here we're going to do a couple other equations and then domain and range based on our graphs. So the red function is our mother function. F of x is equal to the square root of x. That's our parent function. F of x is equal to the square root of x. Remember, we know the shape 0, 0, 1, 1, 4, 2, 9, 3. So our goal is to come up with the equation of the blue function based on its transformation. And the blue function is on the bottom half. How would you describe a reflection across the x-axis? And what would that equation look like? Of course, the equation of a reflection across the x-axis is the square root of x with a minus sign in front. So our function is going to be f of x is equal to negative square root of x. That represents our blue function on the bottom half that has been literally flipped across the x-axis. This 0.11 came down here to a 1, -1. This 0.42 was reflected to 4, -2. This 0.93 was reflected to 9, -3. So now I want to determine the domain and the range, what x values are represented by the blue function, and what y values are represented by the blue function. Again, x values are domains. So I can see that my x value does start at 0. I want to read my x-axis and see my graph continues all the way towards the direction of positive infinity. So I could say that my domain values are going to include 0 because it starts there. And we're going all the way through positive infinity. Keep an open bracket on infinity. We can never actually touch infinity. Now, as far as the range is concerned, remember range is all possible y values, all possible outputs. So what do you think the range is for the blue graph? Again, remember range is y values. So we're going to read the y-axis. Oops, I wanted that in purple. Again, starting at 0, 0, we have our graph here on the y-axis. And now, since it's been reflected, it's going in the negative direction along the y-axis, going from 0 and continuing to negative infinity, right? Pointing down is towards negative infinity. Now, as far as interval notation is concerned, we start with the smallest number first. And if I was going to describe my range, we're going to start with the smallest number. And the smallest number is actually negative infinity. And it's continuing all the way to 0. We're going to include 0 since it is actually defined there. So start with a smaller number. Negative infinity is smaller than 0. So I started with negative infinity and going all the way to 0. All right, let's practice this again with a few more values, a few more functions. So here we have it again. Come up with the equation of the red function and then come up with the equation of the green function. In this example, the blue dashed line, the blue dashed curve is actually our parent function, our mother function, f of x is equal to the square root of x. So take a second and see if you can determine the transformation of the red function and then come up with the equation of the red function. And then similarly, try to do it for the green function. What is the equation of the red function and what is the equation of the green function? All right, so thinking about the red function, right, we notice that our function is changing. It's starting at 0, 0 right here. That's our locator point, and it's shifted over to the right one and down 1, down 2, down 3, down 4. So my locator point of my red function is x is equal to 1, y is equal to -4. I have moved to the right 1 unit and down 4. If I've moved to the right 1 unit, down 4, my function f of x will look like the square root of x. Remember, if I go right 1, opposite would be -1, and down 4, -4 on the outside. For the green function, let's repeat the same process. Again, we're going to start at our locator point 0, 0 right here at the origin, and we'll see where our graph moved. It went over 1, over 2, over 3 to the left 3, and up 1, up 2. So our locator point is now at -3, +2. -3, +2. We can see that our graph moved left 3 and up 2. So our function that represents a transformation of left 3 and up 2 is going to be the square root of x plus 3, remember opposite, plus 3, and then plus 2 as our k value on the outside. So now that we have our transformations, let's discuss the domain of our functions and the range. And I'm actually going to do these ones first because we have another example for you guys to try. So let's focus on our red function, which is the one on the bottom right. F of x is equal to the square root of x minus 1 minus 4. Again, I'm just going to put the locator point down here for our red function again. Remember, this is 1, -4. 1, -4. And the domain of this function, all possible x values for this function. I would read the x-axis and notice that my red function starts at x is equal to 1, right? That's my locator point, and continues towards towards positive infinity. So my function is actually no longer defined at 0, 0, right? At 0, 0, down here at x is equal to 0, I don't touch my graph at all. My square root function is not defined there. So rather, it's going to start at x is equal to 1 and continues all the way towards positive infinity. So my domain of my red function is going to start and include x is equal to 1 and goes to positive infinity. Now let's discuss the range. The range of my function is the y values. We're going to read the y-axis. Notice that my function starts at 1, 4 again, right? Right here. So my y value at this starting point is 4, right? My y value is starting at 4, negative 4 actually, and it's going to continue to rise towards positive infinity. Since my graph is slowly increasing with that curve, it will slowly continue to grow. So my range is going to start at negative 4. My range is going to start at negative 4 and continue all the way to positive infinity. Again, we're going to include negative 4 because that's part of my locator point, and it's going to go all the way towards positive infinity. Sorry, I think I misspoke when I said that earlier. And I actually want this to pop out a little bit more, so I'm going to make it pink. So let's repeat the process for the green function. Let's see what our domain and range is based on the green function. So the green function, again, we're going to start and talk about the locator point. Again, it's at negative 3, positive 2, right? This point right here is at negative 3, positive 2. When describing the domain, which is all possible x values, I need to look on the x-axis where my graph starts. My graph starts here at negative 3 and continues towards the right, towards positive infinity. So reading my x-axis at negative 3 and it goes all the way towards positive infinity, that means that my domain is also going to be starting, all my possible x values is going to start from negative 3 and continue all the way towards positive infinity. Now let's look at the range. The range of it, notice also the domain starts with the first x coordinate. The range is all possible y values. Where does my graph begin? My graph begins along the y-axis at 2, and it slowly starts to grow vertically in the upwards directions towards positive infinity, again, overlapping on this y value, this locator point of negative 3, 2. So my range is going to start at positive 2 and continue upwards, albeit very slowly, towards positive infinity for the green graph. What do you notice about the locator point and the domain and range? What do you notice about the locator point and the domain and range for each graph? Is there a correlation? And see in the next example, if your hypothesis of what you notice is consistent in every example. Okay, again, here we have our mother function, our parent function, f of x is equal to the square root of x in the dotted blue line. What I would like you to do is come up with the equation of the red function and come up with the equation of the green function. The equation of our green function, it has shrunk. Notice that the point that used to be 1, 1, 1, 1, right? 1, 1 right here has shrunk. The height is now approximately 1/2. Looking at the height and seeing that shrink, that tells me that I have an a shrink value attached to my function. So the green function would equal 1/2 the square root of x. And in a similar fashion, the height of the red function, it was at 1, 1. Notice that it has grown, it has stretched by a multiple of 3. So my function, my red function, would be represented by y is equal to 3 times the square root of x. All you have to do is look at the point 1 comma 1 and see how much it has stretched or shrunk down in height. Taking a look at 1/2 x and 3 square root x, 1/2 square root x and 3 square root x, what is the domain and what is the range? The domain of the green function, the domain of the square root, y is equal to 1/2 times the square root of x. Again, notice that the x values start at 0, continue towards positive infinity, and the y values start at 0 and continue towards positive infinity. So both the domain and range for 1/2 square root of x is going to start from 0 and continue until positive infinity, because the x and the y values both start at 0 and go towards positive infinity. And our locator point, as a matter of fact, for the green function is at 0, comma 0. I wanted that to be in green, gosh darn it. 0, comma 0. Now let's evaluate our red function. Our red function, okay? 3 times the square root of x. It has a vertical stretch of 3 square root of x. So again, our locator point is at 0, 0, right here. Our domain is all possible x values for this. It starts at 0, continues all the way towards positive infinity in the x direction. So my domain is certainly going to be starting at 0, because I do have it defined at 0, going towards positive infinity. And my range is all possible y values. So looking at my graph, where does the y value start? Oh, the y value starts at my locator point and continues upwards, because my graph is going upwards. The height is increasing. Here it's at 0. Here the height is at 3. Here the height is at 5. And it's going to continue. This graph right here is going to continue in this fashion, increasing in height, going up towards positive infinity. So my range, all possible y values, is also going to start at 0 and also continue towards positive infinity. So the linkage between domain and range and the locator point is the x value is the start of your domain or the end of your domain, and the range is going to be represented by the y coordinate, either the start or the end of your range, depending on how your function looks, if it's positive or negative. And the final activity for us here would be to graph this function. G of x is equal to the square root of x plus 5 minus 1. How would we do this? We want to employ the same types of steps that the guy in the video did. So step 1, start by graphing at least 3 points of our mother function, of our parent function, f of x is equal to the square root of x. Step 2, use the equation to describe the transformation. And step 3, then apply those transformations to the graph. So why not get started with it? So just by looking at our function, g of x is equal to the square root of x plus 5 minus 1. If I was just going to describe, my goal was just to describe what I see happening on this function, I notice that I have a positive 5 next to x. Don't trust it. Always do the opposite of what your x says. So we're probably going to go left 5. And then I notice that I have a negative 1 k value on the outside of my function. So I'm probably going to go down 1 from my parent function. So yes, h is equal to positive 5. So we're going to go left 5 units, and k is equal to -1. We're going to move down 1 unit from the parent function. But we have to have our parent function graphed in order for us to actually do the transformation. So let's start with that. Remember, on a blank graph, you're going to need to know those 3 points of precision. So the square root of 0 is 0. That would be our first point right here at the origin. The square root of 1 is 1. So at 1, 1, we have this point right here. And the square root of 4, when x is 1, 2, 3, 4, y is 2, because the square root of 4 is 2. That is my parent function, the square root of x. So that is step 1. Start by graphing at least 3 points of our mother function, of our parent function, f of x is the square root of x. Then we're going to use the transformation to actually move our graph. So for me, I'm going to go from inside out. So I'm going to actually move my graph left 5 units. So each point 0, 0 is going to move left 5 units. 1, 1 is going to move left 5 units. 4, 2 is going to move left 5 units. And remember, this is only going to affect the x because x is only left and right, and left and right is also right next to the x value. So here we can see we're about to shift our function left 5 units. So left of 0, 0, 5 units is -5, 0, right? I went 1, 2, 3, 4, 5 units to the left. 1, 1, 1, 2, 3, 4, 5 units to the left. How about 4, 2? Boom, 1, 2, 3, 4, 5 units to the left. Now, we don't have g of x is equal to the square root of x plus 5. We also have a vertical transformation of -1. So now we're going to have to shift our function down 1 unit from the new orange dots. All right, that would be the shift of square root of x plus 5, and we don't actually have that. So now we're just going to move the orange dots down 1 unit. So from this point, -5, 0, we're going to go -5, -1, -4, +1 to -4, 0, down 1 unit. And this dot is going to go down 1 unit to -1, +1. Connect the dots, and voila, you have officially transformed the square root of x to the square root of x plus 5 minus 1. All right, that's all I have for you guys today. Awesome job. Thank you.